Good evening, everyone. My name is Aveen Dayal. I'm a PhD scholar and also a PMRF scholar at IIT Hyderabad, and I will be conducting this live session for week 12 for the course Deep Learning for Computer Vision. Let me just share my screen and we can get started. Yeah, I hope I'm audible and my screen is visible. Maybe if you can confirm in the chat once if I'm audible. Hello? Hello? Uh, Shravanti, can you please confirm if I'm audible? Oh, hello, Shravanti. Okay. I think we can get started with the session. So this is the last week. This is the last course live session which will be conducted for this particular course, week 12. There'll also be another live session conducted by me this Saturday, which will just be a summarization of all the contents and all the lectures which we had throughout this course. So in this class, like always, we will discuss some example problems related to the week 12's content, and we'll also do some code walkthroughs. So in the week 12, we basically discussed about, professor basically discussed in the recorded lectures about self-supervised learning, and then he also discussed about uh, adversarial robustness, and then
Yeah,
can you can you please mute yourself?
yeah. Computer typing, voice computer.
Going back, yeah. So in week 12, professor discussed about self-supervised learning, and then sir also discussed about adversarial attacks, adversarial robustness, basically. And then sir also discussed about few shot learning and different algorithms in few shot learning. So in today's class, we will be basically revising the same things. So I'll start off with few shot learning, then go with self-supervised learning, and then a little bit about adversarial robustness, and then finally do some code walkthroughs related to these concepts. As always, if you have any questions or anything, you can always put it in the chat or raise your hands or unmute and ask me the question. Uh, just to confirm once again, since others have joined, I'm audible and my screen is visible, right? Maybe if someone can confirm in the chat. Can someone please? Yeah, thank you, Jitendra. So coming to few shot learning. So the one major motivation for few shot learning, like discussed in the recorded lectures also, is that usually supervised learning requires a lot of samples for training. It and collection of data samples sometimes is really hard, especially when you talk about cases which don't occur very often in real world. Like in medical domain, you don't get a lot of disease cases, right? Some rare disease cases where you have just few samples, or even when you talk about autonomous driving, where you don't really see a lot. Like most of the data which you see is normal driving scenarios, but extreme driving scenarios like storm or like heavy snowfall or going to different other environmental conditions, those are all data samples which are very less compared to the normal driving conditions. So how do you make your model efficient when you just have few samples available with you. So that is what the entire concept of few shot learning comes into way picture. And then the sir discussed also the setting of few shot learning and how it is different from the normal empirical risk minimization. And also he talked about n way k shot learning, where n is the number of classes you have, k shot learning, k is the number of samples you have, and that is how you define any few shot learning problem. If there is also zero shot where you have no samples available, so during test time only you see a new sample either of the same class or a new class, unseen class, and you'll have to basically predict during the test time only. Or apart from that, there is one shot learning where you have one sample available, two shot, and so depending upon the number n. And coming to that scenario itself, in few shot learning, we usually have these two data sets, which we call meta training set and meta testing set. In traditional supervised learning, we just have training and testing. But in meta training, we combine the train and test. Like if you see over here in the first set of that base set, like the first row of the base set, the one in the first block are all training samples, and related to this particular task only, we have some samples kept aside which we call the test samples. And now this we consider as a task itself, task one. In this case, the task is image classification, so this is the task one. Now in the next row you see a different task, task 2, classifying a different type of birds again. So sometimes it doesn't have to be birds also, it could be something else like some other classes. So in similar way you'll have some you'll have different batches basically available with you in your meta training set, and inside that each batch of task you have your train set and your test set relevant to that particular task. So the goal of meta training is you try to learn a model which is learning how to perform the task rather than focusing on how to increase the accuracy of one particular task, that is one particular row. It is basically trying to learn how to even make my model learn itself when it is presented a new task. That is what we're trying to see. Why is that important? Because in the testing time, which is usually a real world, you have a support set, which is usually the samples which you give during the testing time to your model. And just based on these few samples across these n classes, we wanted to quickly learn the model parameter such that it is going to perform really good in this particular task. So that is why this is called as meta testing, and that is why here we call it as learning to learn, where we make a model learn on how to learn a particular task. So it's also called as learning to learn or meta learning. So to so this field itself is not it's old field. Like there have been so many models which have been proposed over I think more than a decade or so, even in deep learning itself. So as you can see, this is again not a complete exhaustive list, but I would suggest a better classification of all the possible algorithms that are possible for few shot learning. There might be some here and there gaps or missing models, I think, but this more or less covers it. So here in few shot learning, as you can see, you can classify into two different type of methods. One are non-meta learning methods, and the other are meta learning methods, which we just saw. So usually we focus on meta learning methods itself for few shot learning, and non-meta learning methods, they do work, but they don't work very well because they are either too narrow, or like transfer learning is a type of technique. So in transfer learning, what we do is we have an original data set on which we train our model, and then we fine tune that original data set to a new data set which we have collected. So in this case, we don't really worry a lot about, in transfer learning in general, we don't worry about number of samples of that new task or anything. And it's also not really possible for it to do multiple tasks at the test time. Like for example, if it's doing a particular task 1 at test time and now some other task 2 comes during the test time, it will not be able to do task 1. We have to adapt again to task 2. So it's not a great method to do. Obviously there are some hybrid methods with transfer learning which people have done, like MOV, VAE and different methods. But overall, meta learning methods are more suitable for few shot learning. Even in meta learning methods, you have different types, and three main types. Hybrid types are basically across a combination of these three types itself. So the what are the main types? It is metric learning, optimization based methods, and model based learning. So I think in the course, also in the recorded lectures, there was a similar classification like embedding learning and optimization and parametric learning, and I guess model based learning. It's similar classification, but the names are different over here, but the concepts remain the same. So in metric learning, the main goal over here is to learn a similarity metric or between any two samples of your meta training data set. So what it tries to do is the model, it tries to learn similarity when two inputs are given to it. So based on that, it can easily identify, okay, what all the things I know and what all the new things that I don't know when the test time happens. So in a way, we are trying to you can think of learning a cosine similarity function, but in a very high dimensional space. All we try to do is a similarity function we are learning. And whenever two input samples are given, we use this similarity function and we say, okay, is this sample something I've already seen and what is the class? If it's not similar to what I've already seen, then it is something new. Then I'll try to classify it as into a new unseen category. Apart from that, there is the idea of metric learning, and there are many algorithms like Siamese network, matching networks. You can these all things, sir. Siamese network we've previously seen. Matching networks and relation networks. What sir taught in the recorded lectures. You can look into those for a better understanding and in-depth understanding. And then coming to another type of meta learning methods, which is your optimization based methods. So here in optimization based methods, the most famous algorithm is called as MAML algorithm. So we'll talk about what the MAML algorithm in the next slide is. But mostly MAML has actually changed the game for the optimization based methods in meta learning. And over the period of time, people have come up with more what do you say advances of MAML like proto MAML, TAML, and like diff MAML plus plus, and so and so and so. So over here, what we try to do in optimization based methods is we assume that what should be the parameter weights of our original model, such that with each update it can adapt to a new task, but at the same time it keeps a track of what its original meta parameters are. So I'll explain more clearly what it is with an example in the next slide. But for now, you can assume it as learning the parameter weights using a meta learning type of an update. And then model based learning here, uh, mostly for model based learning, you use a memory network, which is usually an LSTM type of a network, where that LSTM kind of learns how to create a new model which will be correct for a particular task which it is given at that particular training or testing time. So you can assume it to be like a memory block, the LSTM. So it keeps on learning and rewriting that LSTM, the memory block. And what it tries to learn is whenever you're given a new task, what should be the model parameters that will perform well on that task. So here we use the help of the model parameters, and we need to know the model parameters by with the help of LSTM block. So that's why it is model based methods. And then like hybrid methods are nothing but a different from different of these three parts, you take different concepts and then you combine them and create a node. I hope this classification is fine. Yeah, if you have any doubts in this classification, it's very similar to what sir has explained. I'll just pause for a quick minute. If you have any doubts, you can ask me now, else I'll move ahead with the MAML architecture. Okay. So coming to MAML architecture, this is like one of the popular algorithms for optimization based meta learning. In fact, this has completely changed meta learning usage itself, and people started like seeing it more like they were able to apply this algorithm across different types of tasks in from classification. They even applied to reinforcement learning, different NLP problems. A lot of applications popped out with this MAML algorithm. So on the left side, you can see the algorithm itself in a what is in a flow chart type of a thing in a data flow manner. Whereas on the right side is the main intuition or the loss function which they use. So maybe first I'll talk a little bit on the intuition, and then we can go to the flow chart of the figure. So seeing at the right figure, you can see that the bold arrow, right, bold mark, which is called, theta basically. So this theta is nothing but the meta parameter. So when your model, let's assume your model, which is the meta model, those parameters are these theta. And now at this particular point, you have different tasks to which it has to adapt. So based on the gradients of that loss function of that particular task, your parameters keep on moving. Like if I want to excel at task 3, then my this theta will move to the right, like it's shown over here, right? Phi 3 star. That will be the optimal parameter of that particular task. So since we want to adapt to that particular task, we'll also move in a similar direction. Similarly, for task 2, the optimal parameter is phi 2 star, and it's in the direction of downwards. So our theta parameter will know, okay, okay, this is my task 2, and then it also tries to adapt by moving towards this side. When I'm task 1, I move towards my left side. So, and after I finish this task, I can come back to my original state, which is the theta parameter. So what this mammal algorithm is basically doing is, we have one set of parameters theta, which is like the main mind you can think. And whenever a new task comes, using a certain gradient of that loss function, it moves in that particular direction. And what is that learning or loss function rule, which is seen on the top? So if you focus on the inside part, so first we'll talk about this loss inside, loss of theta comma d data set, which is the training data set of the ith task. So what here we are trying to do is, we are trying to learn this delta of L3 or L2 or Li. That is what we're trying to learn. And then we first find out the loss with that particular task. We find the gradient of that, and then we update the meta parameter based on the how it is performing on its test set. So the meta parameter needs a double gradient over here. Like if you see, the if you want to calculate the gradient of this entire loss function, we need to calculate the gradient of the gradient. So we need a double gradient, which is called the Hessian of our neural network, basically. So Hessians are usually costly to calculate. So that's when I guess the paper was proposed by Chelsea Finn, I think in 2015. So she came up with a shortcut technique to approximate the Hessian. So if you want to minimize this particular loss function equation, right, which has double gradients to be found out. So she found a technique or trick, you can say, to estimate this double gradient, and then she was able to train the entire meta network in a single go itself. You don't need to calculate Hessians. And how do we do that? You can see the left side now. So we'll talk about the left side figure. So first we have outer learning loop. You can just ignore for now. From each For each task, like the phi 1, phi 2, or phi 3, each task basically we first sample the task, whatever task we want, and then inside the task we sample some case images, and that could be belonging to some n number of classes. And then we repeat this entire inner loop for some epochs or some steps. This n is not the n way k-learn, this is some n number of steps, you can say. And inside this inner step, which we are repeating n times, what we do, we basically do a simple supervised classification task. We take those samples, k samples, we send it to the network, we calculate the loss, we update the networks, and then we repeat the process. So we keep on doing it, and after the k n times we do it, now we take the test sample. If you remember the first figure, each batch has a training sample and it corresponding test sample, right? So we then take this test set, this test set of the meta training itself, and then using the test set, we update the outer parameters, which is the meta parameters, using this loss function on the right side, which you can see. And then after we update, then we go back, we do it for a different task entirely. So very simple architecture. We first have a task at hand. We sample the task at hand. We take some k samples of that particular task. We run the normal model update rule, like we do for supervised classification for n times. And after nth time, we then update our meta parameters using this equation on the right side. And then we keep on repeating it until we finally get our meta parameters, and then we stop our training. So in this way, they were able to not worry too much or depend too much on what the model parameter should be, like the memory-based model, or learn a similarity metric. We're not worried about anything. We just see what is the task at hand I'm having, and how should my meta network, this theta vectors, should adapt or should move in the direction, so that it can perform that particular task. Let me just pause for a quick minute. So I hope this was clear. If you have any doubts, you can unmute and ask me or put it in the chat. I'll just pause for a quick minute. Okay. So I'm assuming there are no doubts and it is clear. Just a second. No. Yeah. So after this, we go to self-supervised learning. Yeah. So in self-supervised learning, what are we trying to do? So in self-supervised learning, we are trying to learn the like let's assume we have unsupervised data. So we try to learn patterns in that unsupervised data, so that we'll be well equipped to perform any type of task, because now we understand how the data itself is being learned, like represented, right? So what I try to mean is we try to underline learn the underlying patterns in the particular data set, which is irrespective of whatever task we have to perform, be it the image classification task or object detection task, doesn't matter. When you're given some data, there are no labels. We try to only create some pseudo tasks, or we call it auxiliary tasks or pretext tasks. And using these pretext or auxiliary tasks, we try to learn what are the different patterns that are even present in the data set. So so that our representations of that particular data set, no longer we need an entire big data set. We'll we'll already have a very good head start, you can say. We'll have a very good beginning to do our particular given task, because now we have used the pretext or auxiliary task to learn the underlying patterns that are present in the data set. So that's what this particular self-supervised learning field even came into picture. So right today, in today's world, is a very popular technique, self-supervised learning. Most of the people use these techniques to like as a, what do you say, a pre-training task. So most of the times when you want to do any task, you need to first warm up your model. What do I mean by warm up is you want to make sure that the initial weights in your feature extractor, like resonate 50 or resonate 100, the initial weights should not be random, because if you start from random weights and try to come down to the optimal, it'll take a lot of time. So instead people say, okay, instead of doing some random weights, why not first let me do a warm up phase where I do some self supervised learning tasks, like the auxiliary task, where the weights which are learned are now somewhat meaningful. So they learn some meaningful representations, and starting from there will reach my optimality for the given task in a faster period of time. So most of the people nowadays consider self supervised learning as a very good pre training step, and most of them use it in their applications, even in when deployed in real world. So why do we need it? So like I said, collection of the data is really a big task in today's world, especially labeled data. Unlabeled data, we have a lot of unlabeled data lying. So you can just crawl the internet and you can get a lot of unlabeled data. Labeling the data is usually very hard, and sometimes labeling also requires a lot of domain experts. Like for more case sensitive examples, you'll need a lot of domain experts and human labor and everything. So to overcome all those things, we try to use these self supervision techniques. And so now we'll talk about different pretext or the auxiliary tasks which we'll use in self supervised learning. And these are again not an exhaustive list. Apart from this, there are again more number of self-supervised learning pretext tasks which people have come up with. But yeah, nevertheless, we can talk about the popular ones. So again, as you can see in the image, you have your input image, which is this foot rugby game, and then we don't send this input image as a whole to the encoder. What we try to do is we first create a mask, like this white mask, which is basically cropping out that particular input image. We send it to the encoder, to this type of architecture. Then we have a decoder, which, and basically this encoder decoder architecture, which is trying to learn what should be filled inside this white color space. And then you obviously have the ground truth with it. You don't need any label over here. If you see, you instantly changed this task in like even though you have unlabeled samples, you can easily change it into a supervised setting by you creating your own labels. Like this mask which you created, which you hid, right? That will become your ground truth label, and then you do use your normal L2 loss function to identify if the ones which are generated by the encoder decoder architecture is it the same as the ground truth. So very simple thing. The only catch over here is we use something called as a channel wise fully connected, whereas in general encoder decoder architecture like UNet and all, if you remember, we use a fully connected network, but here we use channel wise fully connected network. So maybe to keep it more interactive, can anyone tell me why we use channel wise fully connected network over here? uh, why not just use a simple fully connected network between the features of the encoder and the decoder? Why do we use channel wise fully connected networks? Any guesses? You can just post it in the chat, unmute and tell me. Why we actually need channel wise fully connected network is because here when usually the encoder features, right, they are of a high dimensional space. So I think in the paper, as I remember, there are around 1000 plus 1200, I guess the vector dimension is the hidden feature dimension, and you need to have the same 1200 for the decoder. Now the 1200, like every 1200 node in the 1200 list of the encoder should connect with every node in the 1200 list of the decoder. So as you can see, the number of combinations is huge. Whereas if you do it channel wise, so I think when you do channel wise, now you'll have some n cross n maps coming from this encoder, right? So instead of connecting all the maps of that particular encoder feature with all the maps of the decoder, you just connect with that n cross n. Inside that n cross n patch, you connect only that n cross n which is corresponding to the encoder with the n cross n of the decoder. So then you are reducing the number of combinations and computational cost. So because of that, we do channel wise fully connected networks. I hope that was clear. So if I'll just explain once again. So if we didn't use channel wise fully connected, your encoder feature will output an m cross n cross n output from the encoder feature. We'll have a similar m cross n vector in the decoder, and now you'll have to multiply m cross n cross n cross n cross n cross m, which is basically m square n to the power 4. So many number of connections will be needed. That's a huge number. Whereas if you use channel wise fully connected, you'll have the features again m cross n, and here also m cross n, and now you will have to do only m into n square, m into n to the power 4. You'll reduce that entire m square factor over here. So that's a huge reduction in computational cost. So because of that, we do channel wise fully connect. I hope that is clear. If you have any questions, maybe you can just unmute and ask me.
Hey, Vince Vati here.
Yeah.
Number of channels depends on the number of colors in the image, right? If it's RGB image, then there will be 3 channels. Is it like that?
That is for the input, right? You're talking about the input. Yeah, the
Yes.
input. Yeah, input has number of channels, depends upon what type of an input it is.
Okay. But this number of channels will increase in the last layer of encoder.
Yes, number of channels usually we keep on increasing throughout your encoder architecture because we assume that the channels are learning certain type of features. Like one channel can learn something like edges, one channel will learn something like intensity. So each channel will learn a different unique feature of that input image. So we say ki in the neural network, in the encoder CNN network, we always reduce the spatial dimension, that is the height and width, but increase the number of channels so that the model can learn more and more features of our particular input. So that's the usual convention with the encoder architectures. In decoder, we do the opposite, where we start off from high number of channels and small height and width, and we keep on upsampling and until we reach the original height and width of the input image.
Okay, so here the output of decoder is that area where there is a white patch over the input image.
Exactly.
Okay. And it is just trying to reconstruct, is it?
Yeah, basically what we're learning in this encoder decoder is trying to reconstruct or fill in what is missing in this white space. The network is trying to fill in some this gap, and we then how to fill in, like we'll need to have a loss function which will update, right, which saying ki how good is your current estimate, and that loss function is coming from the L2, which uses this ground truth actual mask filling values which are there.
Okay, but in training set we will have both, like original image with patch and the output of that. So there will be two pairs in the input data set.
No, no. Input data set will just have this image which you see along with its ground truth patch. Basically, this is the input image.
There.
Yeah. So any like supervised class, you have x and y, right? So this will be your x, and this small patch is your y, basically.
Okay,
Okay.
got it. Thank you.
Yeah. Any other questions related to this? Okay. So this is just another example again. So you can see these are different output results. So if you used input context, if this is the particular input which we have, and this is the mask which we are creating, obviously a human can do really well. Human For us humans, it's possible because since we know this is a building. Obviously, if there are windows, windows should be coming across because there's a windows. This is the entire one building, right? So we know what the continuity should be, and we can do it really well. And now, when we use just the context encoder, that is using just the L2 loss, we get a image in painting done, but it's not very clear. It's very blurry. So people then said, "Ki, I mean, in the paper itself, they suggested why just stop with L2 loss? Instead, we'll use L2 plus adversarial loss." So maybe now can someone guess or answer why using an adversarial loss is actually improving this? We learned in GANs, right? Adversarial losses are used for generating images. Why is adversarial loss actually improving from this blurred image to a more sharper image? Any guesses? Okay. So if you look into the definition itself of what the adversarial loss should do, right? So if you remember what we talked about in GANs is the space which on which the manifold which the adversarial learning learns is very smooth. What do I mean by smooth is that it can generate from any part of the entire manifold, whereas VA is discrete. Like there are large lumps of mass at certain parts in that manifold, and there are a lot of empty spaces in that manifold. Whereas in adversarial, since we don't assume any distribution, we assume an implicit distribution. We learn a manifold which is very smooth. So generation from a very smooth manifold, you can generate even more smaller detailed images and more higher quality images. So that's why actually using adversarial loss, which is our basic GAN loss, if we use that, the image actually from blurry goes into a more detailed image. Obviously, not as good as the human artist. That is the best possible level, but it's still a lot better than just the L2 loss. And again, here the adversarial loss here, maybe someone can tell me where in the entire encoder decoder, or like the adversarial loss, should it be applied to both the encoder or decoder, should it be applied only to the encoder? Any guesses? Like think of it as a normal GAN architecture. Now if I have a GAN loss, where do I apply the GAN loss? Do I apply only at the encoder, do I apply only to the encoder, or do I apply to the entire encoder decoder? There should be a discriminator somewhere down. You just ignore the discriminator. If this is the generator, where will that GAN loss will be applied? Encoder or decoder, or both encoder and decoder? Any guesses?
I think both encoder and decoder.
Yeah, that's correct. So because imagine it should be both because this is a generator, right? So if you remember the GAN loss, we run it on the entire generator. So this is generating the image, so we apply it on both the encoder and decoder. There will be another network called discriminator somewhere down, where that basically tries to identify which is a real image or a fake image. That you follow your normal GAN architecture, but for this particular architecture, we apply the generator loss on both the encoder and decoder. Now coming to another type of a pretext task called the jigsaw puzzle task. So again, very interesting task here. Again, very simple also. So always remember when you are people keep on creating their own pretext or auxiliary task. So you always remember that when you are generating your own task, keep it as simple as possible, because the goal over here is to for the model is to learn features which are inherently or easily available in the data. If you create a very hard task, the entire point of because that hard task will have very specific representations to be learned. Now you don't learn a representation which can be generalized to any task. Now you're learning representation which are very specific to that particular task. Whereas if you look at this jigsaw puzzle or the previous one also in painting, these are all learning image representations which can be easily used for any type of task in the future you get, like detection, segmentation, or whatever it is you do in the future. So we need to create pretext or auxiliary tasks which are simple so that the model can learn easily, but at the same time, the representations can be generalized to any type of most of the tasks which are commonly used. So, yeah, keeping that in mind, the second task is jigsaw puzzle. So, again, concept is simple. You take your original image, you create different patches of that image, like the green color patches, and then you shuffle this image. Since there are like 9 patches, you shuffle this 9 patches across that object in the image, and all you want your neural network model is to do is how should you make sort these patches in a way such that you come back to your original tiger picture. So it's a simple puzzle solving which we always do, like which we used to do at Skids. We used to give different patches. We used to get different blocks, tile blocks, whatever you call it. We used to arrange those tiles in a certain way that the entire object is making sense or whatever we want the object to be. Similarly, we take that task that we used to do it and as humans and we give it to the neural network to do the same task. We give it different patches of the image and then we ask it how do you want to arrange these patches such that the output should look like an entire object, which is a tiger. To be more specific, this is something what a typical architecture should look like for the jigsaw puzzle task. So you have this particular object called car. So you first create these patches, the green patches of this particular car, and then you create a lot of permutations possible. So you'll have different indices. Sorry, you'll have a set of different indices. Each indices contains a particular permutation. So here we say ki okay, what does permutation mean is like this ninth block comes first, as like here the ninth block will be number one, the fourth one will go to number two position. So that input will change based on the permutation combination we have in this particular index row. So based on that, we give this as an input, and the neural network, like there are several CNN blocks going to each of this particular tile, and the CNN at the end of the day combines all the tiles information together at this part, and then it learns, it outputs what is the particular index number. This will be the index number. It should learn, okay, this is a combination number, this which is nothing but 64. So that is what this is trying to learn. So information is available for it ki what type of a particular input combination is a one particular index number. So based on that, it is trying to rearrange or learn our particular different combinations or how to rearrange the tiles so that the object comes back in the original image. uh, I hope this was clear. If you have any questions you can ask me, maybe. Yeah. Go ahead, Swati, I think. Yeah, ask. You
Yeah.
have a question.
So, what is the application of such kind of this thing framework?
So like I said, so basically these type of tasks are used for a representation learning. Now why do we need representation learning? If you learn a good representation and now I give a complex task, task to you, you can start instead of a random network initialization, you use these representation as a starting point and then you do your task. So to learn good representations from the unlabeled data you have, you use these tasks. So that your neural network basically has a good starting point instead of random weights, right? You use these weights as a starting point and then you optimize it using gradient descent.
Okay, so there is no direct application, but intermediate way. In intermediate way, I can use this as
Exactly.
a representation and feed it to my model for training.
Exactly.
So
Exactly. So these
my
methods.
training set will have only such images, right? And our training set will have only the patches or how that training set will look like?
For this task or in
Yeah,
general?
for this task. For this task.
Yeah, so for this task you will have these different patches with you, and then you'll have the ground truth index, this set basically which index number constitutes which particular combination. You'll have these two as the data available with you, and your ground truth will be your index number, which will be the output from the neural network also. So your y is your index number, x is the set of all these patches basically. Now each patch can be arranged in a different way that is corresponding to your label basically.
Okay, but then this is self-supervised learning, right? But it is somewhat, it is, uh, I mean, it is not that self-supervised, right? We are providing ground truth to this model.
No, this is self-supervised. What see, self-supervised means you are creating pseudo task, pseudo supervision task. Here, ideally, if I give this image, the label should be car. But here, I don't care what the label of this. I just collect this image, and now this set permutation set I am creating. So you, as a like a domain expert, you create this permutation set, and then you give this pseudo ground labels like 0, 1, 2, 3, 4 based on the combination you have on the right side. So here you're not using any ground truth labels of what this image or anything is. Here you're giving some pseudo ground truth labels which you create. And because the task,
In some way, I'm giving ground truth also, right? Supervised learning means we provide some object and we provide label. That is supervised learning.
Yeah.
Here also, in some form of ground truth, we are providing to model.
true.
But we call this as self-supervised learning.
Exactly. Here it is supervised only, but the labels are given by the domain experts or self-supervised.
Yeah, and the earlier one in inventing, sorry, in inventing.
Yeah.
Here we have only this image and we will have the patch here, but there won't be any white space in the input set, is it?
No, this down part is your label, right? This is your pseudo label. If you look at the loss function, the first part is the prediction. The second part should be the ground truth, which is nothing but this y over here, which is your ground truth patch. So here also you are generating a label, right? You're generating your own label by creating a white space in the input, and your label will be that whatever element was there, that particular patch over here.
No, what I'm trying to understand here is input set will have only this image without the patch. That
And
will be the.
no, the input set which the x and y are talking about, the x is this, the y is this part.
This means the image with white patch or without white patch.
The image with white patch is the input x, and the smaller patch which is there, right? Can you see the pointer? Is the pointer visible?
Yes, it's visible.
Yeah. This smaller patch is the y basically.
Okay, and ground this loss will be calculated against this input and output x and y, right?
Loss will be yes, not x and y, the prediction and the ground truth. Prediction is basically this output of the decoder.
Okay.
Okay.
And the same is applicable for that jigsaw puzzle also.
Yeah,
Which is
exactly. In jigsaw, index will be your y, and this entire combination, this will be your x.
okay. Got it.
Yeah, sure. Anyone else? Do you have any question? Okay. So, yeah. So in this way, basically, this is another jigsaw puzzle auxiliary task. And then we can move on to another simple, this is a very simple auxiliary task, which is called rotation prediction, or predicting the rotation of your particular input image. Again, we take your input image to be x, and then here we first rotate it across different angles. We rotate it with 0, 90, 180, 270. What the neural network tries to do is, when you give 0 image, it should predict the output. What is the degree? The y is basically 0. The ground truth should be 0, and the neural network should predict that the ground truth is 0. That is, nothing has been rotated. If the input is 90 degrees rotated, the ground truth will be 90 degrees, and the neural network should predict that the amount of rotation for this input image is 90 degrees. Similarly, 180 and 270. So in this way, you basically you're making your neural network learn where that particular object is present in the entire image because now looking at that particular object's orientation, we are saying whether it is rotated what particular angle. So as you can see here, higher level concepts are learned. So it's a very useful task because you are focusing more on that object in the entire image, and seeing, okay, this entire region corresponds to one particular object called bird, and how is that bird rotating. So where is its starting point, where is its ending point, it should have an idea of that also. So it's a very good pretext or auxiliary task. So I think this is this is clear. If you have any doubts, maybe I'll just pause for a quick second. If you have any doubts, you can ask for this particular part.
So basically, whatever we can do in data augmentation, same auxiliary task we can provide for self-supervised learning, is it?
True,
This is
but
understanding for data augmentation.
true. But certain data augmentations might not really make sense also. Like for example, if you think about changing the colors, right? So it might not, you can do it, but what are you gaining from it? That will be, in this case, it's a very strong auxiliary because you're identifying the objects and rotating. Like even image in painting, if you do it in a smaller patch size, that is actually one of the augmentation type only, where you randomly remove some patches and send the data. So that is also one type of augmentation if the patch size is small. So you can think of data augmentations to be kind of like a pretext task, but which type of data augmentation do you use, that actually matters, because some data augmentation doesn't really help us learn much good representations.
Okay, so then how to determine which one can help us to get better representation?
So that you need to understand what the augmentation is trying to do. Like I said over here, why is this good? Because when you rotate something, you are the neural network is forced to look at a certain part in that image which we know is the object, and it is also forced to look at how this object, where it starts, where it ends. So you're making the neural network forced to look at certain important regions in that image which we know is what the neural network should look at. Whereas if you take a augmentation like color, right, color changing, it doesn't really matter. So if I change the color of this to black, blue, or something else, it might learn some representation, but it's not very useful. Where will we use different colors as a representation or a starting point for task? Whereas over here now, this, if you use representations for any task, we immediately know that the neural network can identify very quickly in an image where the object should be present. So you need to use that intuition of what that augmentation task is doing, and if it's actually helpful in learning some representations with that augmentation task.
Okay, okay, got it.
Yeah. Any further questions regarding this? So moving on from self-supervised learning, after that, the other topic which was covered in the lectures was adversarial robustness. So adversarial robustness, basically what we try to do is we try to create a neural network which is robust to noise. That's our goal. Why do we need to do that? Because if a neural network is not robust to noise, anyone can easily manipulate the way the neural network works. Like these examples which you see below, right? So okay, so maybe forget the text examples. The image example is more clear to understand. So if you have this particular image of panda, and if you only send the original ground truth image of panda, then that original ground truth image of panda can be detected as panda with 57% confidence, which is a good amount of confidence. Whereas if you add slight amount of noise, which is this noise with some like value 0.007, which for humans we still know this is a panda, right? We don't think of this as some other animal. Whereas the neural network, with just this amount of noise, it is able to say, okay, no, this is a different type of a class called gibbon, and that too with a very high confidence. So immediately things have completely changed for a neural network. Although for humans, we as humans, we know these two are the same images of the same class, but uh, because of this small noise, the neural network is not able to uh, be robust enough. So we need to try to make the neural network robust. So for that, first we need to try to see what type of adversarial examples can we generate using this particular ideology, so that we can attack on the neural network. So the more adversarial examples, stronger adversarial examples. When I mean adversarial examples, it means adding noise or corrupt examples. When you generate more and more corrupt or adversarial examples, stronger, and if the neural network is still able to beat them, then we say the neural network is working fine. So now the topic at discussion becomes how to generate strong, corrupt, or adversarial examples. That is what this entire field of adversarial robustness kinds of deals with. So there are different methodologies called white box attacks, black box attacks. So what do white box attacks do is, so if you don't have the access to the model parameters, like for example, if I don't know the neural network's weight, like for I don't know here if you look, I don't know what is the W1 W3 of this. I just know what is the input that goes into the neural network, but I still need to generate a adversarial example. That type of methods are called white box methods. Black boxes, white box has access to the model parameters. I mistook. And black boxes, when the attacker doesn't have access to the model parameters, but it has still tried to generate an adversarial example to fool the neural network. That is called as black box attack. And again, there are some other based on these types of attacks also. Something called as untargeted attack and something called as targeted attack. Untargeted attack, our main goal is to make the model misclassify the adversarial image. So in this case, what is our main goal? We just want the neural network to misclassify this image as not a panda. It could be something else. It could be animal A, cat, dog, or this gibbon, whatever it could be, but it should not be predicted as a panda. That is our goal in untargeted attacks. In targeted attacks, we want it to predict particular class which is not the true ground truth class. So what it means is, we want this particular image, we need to create an adversarial image which makes the neural network say that it is not a panda but a gibbon. So we are saying ki it should target what type of a failed classification also it should do. So that is why we are targeting what fake or wrong classification the neural network should do. That's why it's called targeted attack. I hope the different taxonomies are clear. If you have any questions, maybe you can unmute and ask. I'll just pause for a quick second. So coming to our first method, which is a popular method called fast gradient sine method. So in fast gradient sine method, it's very efficient also because it's just a single step method. All we try to do is, we obviously have our input x and we'll have our ground truth label y. We can calculate the loss, and even that's how the training of the neural network also happens. So we have the loss calculation, then we have the gradient, we calculate the gradient, and then we back propagate to update our model weights. What the FGSM model says is, when you calculate the gradient, you use that gradient, the sign of that gradient, whatever plus or minus we get from the gradient, and then you add that with some epsilon value, which is usually zero point 0.0 something in that order magnitude. You take the sign of the gradient, send it to the epsilon, and you add it to your original image, and that's how you create an adversarial example. So why is this helpful? Because you are trying to move away from your actual predicted values. Like for example, if the loss function is zero, close to zero, otherwise, it means that my model is able to predict correctly. Now, if my model is able to predict correctly, I need to make my input x to move in the opposite direction of the gradient so that now my model will predict wrongly, because the loss value will increase, right? So that's why we move opposite. So because the loss will be less, the gradient will be less, this magnitude will be less, so we move opposite to that. So that is why this is an efficient method. So we're in a very simple way, we are looking at the gradient sign. If it is decreasing, go in the increasing side, and then you can easily manipulate your particular input image. In case of targeted attack you want to do, so this one is untargeted. If you want to do a targeted attack, you take a negative sign, you subtract from the gradient of the x and the targeted class which you want. So maybe can anyone guess, or can anyone tell me why should we subtract over here? Why should we subtract with this particular loss function x and y target? Same logic of gradient intuition which we used over here. If you can use over here also, but maybe if someone can unmute or write it in the chat. Why do we subtract it over here? Here we subtracted because obviously the targeted class will not be the same as the true class. That's what the targeted attack says. The target class should be different from the true class. That is the first condition we want. So this loss will anyways not be closer to zero. It will be high loss. Now, when you take the signature, when you take the gradient of this, it tries to move to the actual class. But we say ki don't. We go in the opposite direction. That's why we take the negative of this. We don't want to go into the direction of the true class, but we want to go into the direction of the targeted class, and that's why we subtract. So that is why this targeted x we actually subtract it over here. So I hope this was clear. If you have any doubts, you can ask me over here. Unmute and ask. And then coming to another method called projected gradient descent. Again, what this method is, it's more complete than FGSM. So what it is trying to do over here is it takes step till the point has found the adversarial example. Like we create a ball, small ball, L2 ball, or you can just call it a normal ball, neighborhood, you can say. And then if my initially sample was here, we keep on moving to places until we find a particular space in the point where the model adversarial example from this particular part is able to fool the neural network. Now if I sometimes go away from this small neighborhood, we again project it back into the particular neighborhood. That's why it's called projected gradient descent. We always stay in the neighborhood a certain radius, and if you're going away, going out of this certain radius, we come back by projecting it back into the designated neighborhood, and we keep on circling inside this neighborhood until we find an example, adversarial example, which will fool the neural net. So this is projected gradient descent, and this is fast gradient method. So apart from this, nowadays adversarial robustness, actually the field is kicking off. A lot of new methods, a lot of new techniques have come, but these are one of the starting and most popular methods that was used in this field. But you can always look into more and more recent literatures which actually talks about more advanced methods to create adversarial examples. So I'll pause for a minute. If you have any questions for the entire all any concept which we discussed today, you can ask now. If you don't have questions, we can move to the code walkthrough. I'll just pause for a quick minute. If you have questions, you can unmute or put it in the chat. Okay. So if there are no questions, I think we can go with the code. So, in this, I wanted to discuss a little bit about the self-supervised task, which is the image in painting task. So maybe I'll just quickly, okay, maybe I'll just one time quickly go back to what the task was so that you refresh your memory. Okay, this was the task what we wanted to do. So we had a encoder decoder architecture. The input would be the image with the mask, this white color mask, and then we send it as an input to the encoder decoder. Whatever your output prediction from the decoder will be, that is sent to a L2 loss, and the ground truth will, whatever patch of that image, that is the ground truth. And we use the L2 loss to find out what is the loss and back propagate to train the encoder decoder. Along with that, we'll have a discriminator network in the bottom over here, and we use the GAN loss to also update the generator to make the images more sharper. So this was the image in painting. Now let's see how we code it in PyTorch. So as always, we need to import our necessary libraries. I think by now everyone is clear of what each of this part does. Like first is just importing PyTorch as it is, and then torch.nn. Nn is a mod. Nn is short for neural network. So inside PyTorch, you have inbuilt how to create your linear layers, convolution layers. All of those layer, what you say, classes and layer functionalities. Those are all present in uh, library. And then torch.optim, this is again used to access all of your different optimizers, which is either your Adam optimizer or your different SGD with momentum or just SGD or any kind of optimizer. All of these are present in optimizer library, optim library. And then, sorry, Torch Vision is used for importing data sets and transforms, which is basically you create how to upload your data samples into PyTorch using data sets, and different augmentations you can do on these particular input images, that is through transforms. And apart from that, variable, you can, it's just like normal variable creation. And then apart from that, you create data loaders. Data loaders are used to create batches in your entire data set, like it based on the batch size given your entire data set, it creates batches. And then also data loader is used to load the particular batch onto the GPU for training and updation of the neural network, and again sends it back to the secondary memory. Okay, now we first talk about the main architecture, which is the context encoder, and which is this encoder decoder architecture in the image which we saw previously. Obviously, so as usual, we use standard techniques for creating PyTorch. If you remember, I talked, there are two types of methods in my previous live sessions. I told about there are two types of method to create a neural network. One is you can use an nn.sequential, which is what we used here. If you want to access intermediate outputs, you don't use nn.sequential. You create each layer, you create a global variable for each layer and call it in the forward function. Since we don't want intermediate layers of outputs, so here we just used nn.sequential. So in the context encoder, like you saw, you create an encoder architecture and a corresponding decoder architecture. So we first create the class called context encoder, always inherit from the nn.module. This basically tells PyTorch that this is a neural network. Whatever you're creating in this particular class, it is a neural network. And whenever you inherit this nn.module, it will require it will require one function for sure, which is forward function. There is another function called backward, which you don't worry about unless you're creating your own backpropagation algorithm. You don't worry about, but most of the times, 99% of the times, you'll just use forward function. So whenever you create a neural network and inherit this nn.module, you always need to also create inside that class a forward function which will tell the PyTorch what should this neural network do. Like, given an input to this particular neural network, where should that input go and what should be the output of that. So that is what this forward function does. So if you look in depth, so we first create the encoder layers, which we name it as self.encoder, which is a global variable. We create, I guess, one, two, three, four convolution layers. And each of the convolution layers, if you look at it, we are increasing the channels. Like someone asked a question, we keep on increasing the channels across after each convolution layer in the encoder. With this increasing channel number, we make sure that the features learned are more diverse and more efficient than it's able to learn more and more diverse features. That's why we keep on increasing the channel numbers. Kernel size, most of the times you can keep constant. Uh, I think you don't need to vary it unless you have a certain type of spectrogram data or something. You can always keep it 3x3 square kernel size or 4x4. That should most likely work. And then stride also, it depends. These are all hyperparameters which you can play around and see which is working for your data set. There is no one rule which can say this is the way it should do. This is the way you should set your values, because each data is unique and each data will have its own hyperparameter values. You should always play around and see. But standard ways, you can always set kernel size 3 and stride 1 should perfectly work. In this case, we actually took stride 2 and kernel size 4 for this particular data set. And with then we create the encoder layer. And after each encoder layer, if you see, there's a non-linearity ReLU also. And then we create a consequent decoder layer. Now the decoder layer will be using transpose convolution, and as explained in the segmentation week, I think it was week 7 or some week 7, I think week 6 or week 7. Conv transpose basically does the opposite of what a convolution does, that is upsample. So in a normal convolution, your after convolution, your input image height and width reduces because of convolution. Whereas in con transpose, you do the opposite, which is upsampling. So you take your input height and width, you do deconvolution or transpose convolution, and you increase the height and width of the image. And always make sure when you create encoder decoder architectures, the correspondence is the sequence is the same. What I mean by that is, if you look at the channels, we start off with 64, 128, 256, 512. So now the decoder will also get the input from 512, and then you need to keep on decreasing in the same way as you increase in encoder, like 512, 256, 128, 64, and finally 3. 3 will be the output. And then you use the sigmoid. Here we used the sigmoid to basically find out out of all the three channels which one should use should be one or value between 0 and 1, basically the intensity value of the RGB channels. That is why you use a sigmoid. So yeah, so after you create your self.encoder and self.decoder layers, you simply just call it in forward function. It's just two lines. You get your input x, you first send it to encoder, the output, which is again x, is sent to the decoder, and final output you return it from the neural network. Now this will fine for the context encoder, which is this architecture. But I said, like I said, we also have a adversarial loss, means we need to have a discriminator also somewhere down. So that is where we create now the discriminator layer module. Basically, this is the discriminator model. Again, the discriminator model, it will take the features from after it'll take your original image X, and then it is trying to basically identify which is the real image or which is the fake image. So that's why we have a classifier also. We first have the features which will take that input image X. Same again, whatever upsampling you used to do in downsampling you used to do in encoder, we do that. And then we have a leaky loop layer finally attached, and then we have a classifier which will take the output from this features and then identify it as a real image or a fake image. So this discriminator is a standard GAN discriminator which we used in when we discussed about GAN lectures. So as you can see in the forward function also, we do the same thing. We take the X input, we send it to the features, which is this entire layers, different layers. The output is then flattened out and then sent it to the classifier, and the classifier will return whether it's a fake image or a real image. So I hope these two networks are clear. Maybe I'll just quickly pause, and after that we can go to the training loop. uh, any doubts in how these two different classes are created, what is the logic and everything? I hope it's clear. Maybe I'll just quickly pause. Any doubts you have, you can unmute and ask. Moving on. So now, once you create your neural networks, next thing is obviously you're defining a training loop. Again, standard training loops. If you by now you should know that whatever neural network you create, training loop follows a simple template. First template will be writing your outermost for loop, which is your epoch loop. Then inside for loop will be for each batch in that total number of batches. And then, like always, you first you sample the data x and y. The basically you sample each batch, send it to the neural network, get an output, calculate the loss, then calculate the gradients, back propagate the gradients, basically update your neural network parameters, and then you calculate your training validation loss, and then you keep on repeating until you finish both the loops. Standard template is across any neural network you use, unless there are some other modules in between. Most of the time these are the standard inputs. So in this case also very similar, but like I said, here it's a self-supervised task, right? So the ground truth, the label will be your own mask, which will be your actual cropped image of that. So for that we have to create that over here. If you look over here, what I mean by that is, so in this data batch which we sample from the data loader, so from the data, we just take the image. We're not taking the label of that data. We are assuming we don't have the label, so that's why we're not taking the label. We're just taking the image, and then we create a mask. Now this mask is, as you know, the image values are lying between 0 and 1. 0 is black and 1 is white. Maybe I might be wrong also, but let's assume 0 is black and 1 is white. So the mask will also will create a small torch dot zeros. Like this basically creates an entire matrix of 0 images of the size of whatever the image we have, which is 224 cross 224 cross 3. And then out of this particular zeros matrix, we set certain values for the 16 to 48, which is the height, and 16 cross 48, which is the width. So these many particular elements in that matrix, we set it to 1, and then we subtract it 1 minus. So now everything, you're creating a mask. So in this way you created a masked image. So I hope this was clear how we create the mask image. We basically create a temporary zero matrix. We find a small patch, in this case the 16 to 48 is that patch in height and 16 to 48 in width. Both combined will create a small 2D matrix, and that is the patch which we are creating, and we subtract it to get our masked image. And then this masked image is sent to our entire model, which consists of your decoder, encoder, decoder. This is not the discriminator; it just consists of the encoder, decoder. And this masked image will send the output, which is your generated image for that particular patch. And once you get the output for that particular patch, we then take this. Uh, okay. For now, this generated image, you keep it over here, and we now next focus on the discriminator. This generated image, we have the real image. We calculate L2 loss, which is down. I'll show you that. But for now, we'll look at the discriminator, where we first create labels. Real labels are all 1, fake labels are all 0. And then we always send it the image to your discriminator, and then we also send the generated image to the discriminator, and we find out which one is the fake loss and which one is the true loss. That is this over here. Real loss plus fake loss is the final discriminator loss. And here, if you look at the reconstruction loss, this is your L2 loss. This criteria is nothing but your MSE, which is your L2, and you find the L2 between the generated image and the actual image. And then you combine these reconstruction loss with the discriminator loss, and that will be your total loss. And then we do your backward and dot step. So I hope this was clear. If you have any questions, please unmute and ask. After that, I'll ask you some few more questions to make it more clear. If you have any questions, maybe you can unmute and ask in this training loop. It's pretty straightforward. Basically, first part is we create your until generated image. I think it's clear. The discriminator, we use a standard GAN discriminator, where we create labels like real and fake labels. We send both the images, the actual image at this step. Sorry. At this step, we send the actual image. We calculate the loss with that actual image. We send the generated image to calculate the fake loss. We combine these two losses to create the discriminator loss. Similarly, we have the reconstruction loss here, and then we combine these two to create our final total loss. And then we use update backward and step. So just a quick minute pause, and maybe if you have any questions, please ask me. Okay. So maybe I can ask you again. These are things I've previously also explained, but just to reiterate the point. What is the difference between the dot backward and dot step? Why do we have to use both? Maybe can someone say? So we calculate the total loss dot backwards, and then we are again saying optimize the dot step. What does these two step do? Maybe can someone unmute and or post it in the chat? What do you think these two things do? Do we need both the things, or can only one of the thing work? Okay, maybe I'll explain. So, dot backward basically it first calculates the loss and tells PyTorch to calculate all the partial derivatives and the gradient with respect to the loss. So, if you remember back propagation, we need partial derivatives after each particular layer. We keep a track of all the partial derivatives that are happening. So, basically, backwards basically calculates the loss and tells PyTorch to get ready with all the partial derivatives. Dot step is basically the update, which if you remember the gradient descent, we update, right? Theta is equal, W is equals to W minus the learning rate into the gradient. So that update is basically done with dot step. So that is the difference between dot backwards and dot step. And another thing was always make sure whatever optimizer you have. In this case, we have the optimizer underscore G. We always set it to 0 grad. Make sure you always set your optimizers initially before calculating to 0 grad. This is so because when you do the dot step, we make sure that there are no gradients coming from the previous time step. Like sometimes you might not set sometimes there might be some garbage variables present in that optimizer. So to remove that possibility, you first set to 0 grad. This makes sure that all the gradients are now 0, and then when you do this step, you're actually using the gradients which have been generated in this step and not any lingering or pseudo or garbage gradients from the previous step. So that is another important step. Use zero grad. And then yeah, these are just once you create all the important things, now you just actually load the data set and everything. Like for example, you set all your hyperparameters, like what is your learning rate, what is your batch size, number of epochs, and what should be your subset size and everything. And then you load your data set. In this case, we use the CIFAR 10 data set. You can use any data set. Also, you normalize it and you can do tens. You have to convert it into tensor. Then yeah, so now you create an instantiation of your context encoder and your discriminator. Now you also create your optimizers for both your generator and discriminator, and then you train your model. So you can just here we just did it for 5 epochs. You can just keep on training and look. So in this way, you basically complete your in painting self supervision task, and your model once after this training is done, the weights whichever you learned, right, those are very useful representations, and it can actually be used as a starting point for your actual other tasks which you wanted. So any questions in this? Okay. If there are no questions, then we can go to the other code. So in this code, we talk about the adversarial robustness. So we talked about what adversarial examples should do, and one such method which was important was FGSM or fast gradient sign attack. Uh, so what? I'll maybe show the equation. Yeah, we can look over here the equation. So this is what the main equation is for FGSM method. So here what we try to do is once you get a gradient of that particular input sample X, we then make that X to have some noise. And what should that noise be? That noise should be some, this could be some magnitude, doesn't matter, but the sign should be what the gradient sign is. So we try to move away from it. So in that way, we basically use this epsilon and we push our X to go away from what it is predicting. That is basically predicting it wrong. That's what we want to do. So this is the FGSM method. So same inside, everything else remains the same. What the creation of neural network and everything, all the things that we do differently is that particular equation which I showed. You can always read more in depth about what each of this, what the method is doing and everything. But for now, I'll just discuss the main major code block which we use, which defines FGSM, and you can always look into this code and you can let me know if you have any questions. So as usual, these are all again the important libraries which I just explained, the different torch libraries, the data torch vision libraries and everything. So here the main thing is setting of the epsilon values. We have different epsilon values. Again, it's a hyperparameter. You can always see, you can always check which one is working for you. And then also here we assume we take a pre-trained model which is pre-trained on MNIST dataset, and this use CUDA is just to send the data set to send the model and the data set to the GPU. But the major two things are major important thing is epsilon value. That's a hyperparameter which you keep on which you set and which you make sure that whichever is working, which is creating more stronger adversarial examples. So first we create a simple neural network model which will be under attack. The neural network model is a simple LeNet model. You can look into this particular example to look at what the LeNet architecture should look like in the official paper. But this is the architecture. You just create uh, two simple convolution layers, a dropout, and two simple linear layers. So if you look at it, this is your forward function. You send your input to your convolution layers and max pool layers. First you do a convolution, then max pool. Similarly, max convolution, max pool, and after that you use your dropout and you send it to your fully connected networks. Have a dropout, send it to your final fully connected network, and then you have a softmax. Simple architecture, linear architecture. We train it on the MNIST dataset. Okay, and then we finally finish the training, and yeah. Yeah, sorry. Here we load the pre-trained data model of the LeanNet. So instead of training on the dataset MNIST, we already use the pre-trained weights. You can load the state dictionary is basically used to load the pre-trained weights of this LeanNet model, and we load it. And after that, now we start looking at how the attack itself works. Now, this should be the perturbated image, which is your adversarial image. So as you look at it, the adversarial image is nothing but your original image plus the epsilon into the sign of the gradient. So that is what you try to write in the code also. You have your input image, and then this input image you've added to the epsilon into the sign of the gradient. So data gradient is the gradient which you get from the loss function. I will show you how it works. And then once you get the sign of the gradient, we just multiply it with epsilon, add it to the image, and now you return your perturbated image. Okay, one other important detail which obviously the equation doesn't talk about is you clamp your perturbated image between 0 and 1. Maybe sometimes after multiplying and adding, the value can go beyond 1. So it's highly important that it should stay within 0 and 1, otherwise it doesn't become an image anymore if it's going beyond 1. Because always we normalize the values of our input image between 0 and 1. So make sure it always your perturbated image or the adversarial image also has values between 0 and 1. So now you test that basically. So yeah, this is a major part of the code where you test. You first collect all the gradients. You collect the gradients of using the sorry. Yeah, you collect the gradients data.grad.data. Basically, data.grad is for this particular input images of the data. What is the gradients? Dot data is the magnitude of those and signs of that. It will come in a particular structure that will you output using dot data. And once you get your data grad, you send it to the function which you just created. You have your input image, you know your epsilon value, you know your data grad, and then you get your perturbated image. Now, if you check, if you send this perturbated image or the adversarial image to your model and check whether it's actually predicting what it used to predict previously, it won't. So you can just check it in this particular. This is a simple check case where you output your model and output is passed to softmax, and then you check what is the label of that particular softmax, which is the maximum, and then that will be the label, and you check whether it is the actual label or not. Yeah. So used on different epsilon values, your test accuracy changes. So if epsilon is 0, means we are not doing any attack at all. The accuracy was 98.1. But when we started attacking, the accuracy is actually dropped. In fact, so if you use epsilon 0.3, accuracy went to almost 0 percentage. So this means that the model is not at all robust to adversarial examples. So this LeanNet model, if someone wants to attack it, they can easily attack with just using this simple one line equation, and you can completely make the model useless with almost 0 percentage. So you can always see in terms of plot also. And if you want to look at the examples itself, how they are generated, right? So if you plot and see, you can actually, for a human being, you can still see these are all fine. I can still say this is 6, you can still say this is 4, I can still say this is 1. But for the LeanNet model, everything changes. Like it doesn't look like 7 for it, it looks like 8 for it anymore. Previously, where there was no attack, right? It was able to predict everything correctly. But when there is attack, everything changed. But for humans, we can still say these are all letter digits which we can recognize. So this is where you know that neural network models are not at all as not at all good as humans. I mean, like they're so susceptible to these noises basically. So I went through this code a bit fast, but major chunk of the code, like important part of the code, is just this function itself. Remaining all is a standard LeanNet model. So if you understand how to write this function and where to use this function, is these three lines where you collect your gradients and you send it to that function. Everything else remains the same. So that is a major part of this adversarial robustness. So you can always look into the code and get back to me if you have any questions. Are there any questions, at least for now, in what how we defined the FGSM function or anything? If you have any questions, you can unmute and ask. So yeah, there are yeah, 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 sure.
Can you hear me?
Yes, yes, sure.
Basically, we are introducing noise and trying to make it work.
No, so in this case, we are trying to identify what are the strong noise examples which we can create. So we can basically make sure the task of this is basically to make sure that your neural network doesn't get good accuracy. Here we don't want to get good accuracies because we want to show how susceptible the neural network model is.
Oh, okay.
So, yeah, I mean, the field itself, basically, there are two people working. One creates adversarial examples, and the other tries to create robust models which will work against which will work even if these adversarial examples are prepared. So, why is this field important? Because if you don't have strong adversarial examples, you don't know where your model fails, right? So, we also need to learn an entire field where we have to know what type of an adversarial example to generate so that we can find out the faults of the neural network.
Yeah, yeah, okay. Yes.
Yeah. Any other questions? Okay, then. This is what I planned for explaining in this live session. If you don't have any further questions, thank you all for joining the live session. If you have any questions, I'll be on the call. You can unmute and ask. Yeah, thank you all for joining. So no, in general, like you can see, this is a typical neural network. LeNet was actually one of standard neural network in 2013 and 14, 15 time basically. But as you can see, it's not robust. So people come up with different techniques, different augmentation techniques or different other techniques. Like during training time itself, they generate samples with a bit more noise so that the neural network is more robust. So people try to do different techniques to make it robust, but inherently neural network as it is not robust. If you just create a simple neural network without any other modules, it's not robust.
I have a query. Like
Yeah.
it's related to this. Basically, it's about the research work I'm doing. I'm doing research on medical images, and I've been doing uh, I've been using CNN and VGG16 and all those things, as well as Inception V3. But a lot of people are advising me against using CNN. They're saying Transformers is a new thing, and we have to do something on the Transformers for future work. So, do you agree to this, or will it work with Inception and VGG16? What's your opinion on this?
So I would suggest if your model right now for the task which you have, if Inception ResNets are working, I would suggest go with it. Maybe you don't have to worry about transformers for now, because one problem with transformers is the training time is a lot. Like it needs a lot of compute capacity. Obviously, people there are people who are working on reducing that, and they have done a very good job at reducing. Nowadays, there are models in medical field only where you can deploy it in edge computing devices. Maybe you can look into mobile VIT. So those are
Uh,
mobile mobile VIT.
Mobile VIT.
Yeah.
Okay, fine. Okay.
So these are like lightweight transformer models.
Okay.
But if your model, if your task is able to be what do you say, if your task is performed with the standard CNN models, I would suggest just use CNN. If it's not getting good accuracy, then I would maybe suggest transformers. You can maybe start with lightweight transformers, because as I know, I think for medical images and all, like your deployment will be on edge computing devices, right?
Yeah.
Yeah. So if you use a big VIT type of network, maybe it will be slow on edge computing devices. So that's why you can start looking for mobile VIT, which are meant for edge computing and medical type of an applications.
Okay.
Yeah. No. True. But you can always look into this entire field of attacks, adversarial robustness. So I think maybe I think even differential. Uh, I'm not sure of the name. It's called differential privacy. I think the field name, differential privacy and adversarial robustness. You will find an entire set of algorithms which are only working with these images. Okay, then if there are no further questions, I'll end this session. Thank you again once again.
Thank you so much.